Welcome back to another deep dive. Every time you step outside on a clear evening and you look up at those thousands of tiny glittering points of light in the night sky, you are actually looking at billions of invisible worlds,
Yeah, it is. It's really staggering when you look at the statistical models now, because they tell us there are mathematically more planets out there than there are stars.
which is wild because, for like 99.9% of human history, we couldn't prove a single one of those worlds actually existed.
Right, we were completely blind to them.
Exactly. So the question of whether our solar system was just some kind of cosmic baseline or if it was a total freak astronomical anomaly, well, that was entirely confined to philosophy or, science fiction writers.
But today, that paradigm has just violently shifted. I mean, we don't have to wonder anymore.
No, we don't. And that's exactly the mission of today's deep dive. We are going to explore the mind-bending, honestly kind of impossible detective work that astronomers use to actually find and measure these alien worlds. Because when you look at the raw physics of trying to see a rock light years away,
It shouldn't be possible.
it really shouldn't.
The obstacle really cannot be overstated here. We are dealing with an ultimate problem of contrast.
Right.
Planets are intrinsically dim. They produce no visible light of their own, they only reflect the light of their host star.
Right, like the moon reflecting our sun.
Exactly. But stars, meanwhile, are these massive nuclear furnaces that are overwhelmingly bright. So we are trying to observe a very dim, non-luminous object sitting immediately adjacent to a blindingly luminous one.
And the source material we're working from today has a really fantastic way of contextualizing that contrast.
Yeah.
It's like standing in the middle of New York City, looking all the way across the North American continent to Los Angeles, and trying to spot a single tiny firefly.
And that's hard enough on its own.
Right. But it's not just a firefly sitting in the dark. That firefly is crawling directly on the glass of a massive stadium-sized searchlight that's pointing straight at your eyes.
Yeah, the glare of that searchlight completely overwhelms any optical instrument. I mean, the faint photons reflecting off the firefly are just utterly washed out by the billions of photons blasting from the primary light source.
It's like trying to whisper next to a jet engine.
That's a great way to put it. Any conventional telescope simply looking for the planet itself is just going to be blinded.
Which means we can't look for the firefly.
No, we can't.
So if the blinding light of the star is the problem, the ingenious workaround is to actually use that light to our advantage, right? We stop looking for the planet and we start looking for its shadow,
Which brings us to the most prolific planet hunting technique we have.
the transit method.
Yes, the transit method. And the foundational logic here relies on incredibly precise photometry.
Which is just the measurement of light, right?
Exactly. We monitor a star and we wait for a planet to cross directly between our telescope and that star. When it does, it blocks a minuscule fraction of the starlight, casting a shadow across our line of sight.
Okay, let's construct an analogy here for the listener so we can really get a sense of the scale, because it's not like a solar eclipse where the sky goes dark.
Oh, not at all.
Imagine you are staring across a vast, pitch-black field at a giant street lamp.
Yeah.
Way out there in the dark, a tiny mosquito flies directly in front of the bulb.
From your vantage point across the field, your naked eye would never register the mosquito.
The physical object is just way too small.
Right, and the light is too intense. However, if you had a highly sensitive photometer pointed continuously at that bulb, you would capture a momentary anomaly.
A little dip.
Exactly. The total light output would drop by a microscopic fraction for the exact duration the mosquito was silhouetted against the glass, and then it would return right back to its baseline.
And we're doing this on a cosmic scale with hardware like NASA's legendary Kepler Space Telescope and now the newer TESS spacecraft.
Yes, but the operational reality of pulling this off is just staggering. Because these telescopes aren't just glancing around the sky, they have to stare unblinking at hundreds of thousands of stars simultaneously, day in and day out.
Because if you look away for even a few hours, you might miss the mosquito.
Continuity is absolutely paramount. Astronomers plot this continuous measurement of a star's brightness on a graph to create what we call a light curve.
Okay, I like her.
Right, so a stable star produces a relatively flat line on the graph. But when a transit occurs, that flat line exhibits a distinct U-shaped dip.
So the light drops, it bottoms out as the planet fully silhouettes.
Yep, and then it rises back up to the baseline as the transit ends.
But the geometry here has to be so specific, right? I mean, this only works if we win the cosmic lottery and the planet's orbital plane happens to be perfectly edge-on from our perspective here on Earth.
Yes, that is a huge limitation. If the planet orbits flat relative to our line of sight, it crosses the face of the star. If it's tilted even a little bit, it misses the star from our point of view entirely.
But assuming it does line up, I'm curious about the actual data we get from this. When we see that U-shaped dip in the light curve, what physical properties of the planet does it actually reveal to us?
Well, the most immediate piece of data is the planet's physical size, specifically its radius relative to the star.
Because a larger object blocks more light.
The math is beautifully straightforward in that regard. A larger object casts a larger shadow. So if we look at a gas giant comparable to our own Jupiter transiting a sun-like star, we see a dip in the light curve of roughly 1%.
Okay, 1%. That is a tiny margin, but I assume our modern instruments can handle that pretty comfortably.
Oh, easily. But what happens when we scale down to an Earth-sized rocky planet?
Oh boy, I'm guessing it gets a lot harder.
The difficulty scales up exponentially. An Earth-sized planet blocking a sun-like star creates a dip of only a tiny fraction of a percent. We're talking often around 0.001%.
0.01%. Wow.
Yeah. Distinguishing that microscopic dip from standard instrument noise, or even just the natural flickering of the star itself, it requires a level of engineering precision that was borderline science fiction just a few decades ago.
Okay, so we established the size,
Mm-hmm.
and because planets are locked in a predictable orbit, that dip repeats over time.
Right.
So we also get the orbital period, or the length of the planet's year, just based on the time between those dips.
Exactly.
But I have to push back on something here. Measuring a shadow basically just gives us a silhouette. It tells us the size of the rock and how fast it goes in the circle. Yet our sources for this deep dive indicate that we are actively figuring out the weather patterns and atmospheric compositions of these planets.
We are, yes.
Jumping from a 0.01% shadow to an alien weather report seems like, I don't know, an impossible leap in logic. How do we extract a climate from a simple silhouette?
I get why that sounds impossible. The key to making that leap lies in realizing that the shadow isn't a completely solid, hard-edged cutoff.
What do you mean?
Well, when a planet transits, the vast majority of the starlight is blocked by the opaque, solid bulk of the planet itself. But if that planet happens to have an atmosphere, there is a very thin, translucent outer ring encircling that solid sphere.
Okay, so the air around it.
Right. And a tiny, tiny sliver of starlight grazes the edge of the planet and passes directly through that atmosphere before continuing on its path to our telescopes.
Oh, I see. So that thin halo of gas basically becomes a chemical filter.
Precisely. And since we know from the field of spectroscopy that different chemical elements and molecules absorb very specific wavelengths of light, that starlight is going to be fundamentally altered.
So we take that filtered starlight and we run it through a spectrograph.
Yes, which is an instrument that disperses the light into its constituent spectrum, basically turning it into a rainbow.
Right.
We are looking for absorption lines. These are specific dark bands in the spectrum where the planet's atmospheric gases literally swallowed the light.
So we aren't just looking at the total amount of light dropping anymore. We are looking to see if, say, the red light dropped slightly more than the blue light, or if a very specific wavelength of infrared is missing entirely from the rainbow.
Exactly. Molecules like water vapor, carbon dioxide, and methane, they each have unique quantum structures.
Okay.
When photons of light with the exact right energy level hit those specific molecules, they are absorbed. So by mapping out exactly which microscopic slivers of the light spectrum are missing when the light finally reaches, say, the James Webb Space Telescope,
We can match those missing bands to the chemical fingerprints we have already mapped in laboratories right here on Earth.
that's it exactly. We call this transmission spectroscopy.
Transmission spectroscopy.
And it is arguably the most powerful analytical tool we have right now.
It's honestly mind-blowing for me as a host to try and convey this to you listening. We are sitting in our own solar system, catching a few stray photons that filtered through a cloud layer trillions of miles away, and declaring with absolute certainty that it is raining methane or that the atmosphere is choked with carbon dioxide.
It really is wild. It fundamentally upgrades our capability from merely cataloging the existence of planets to actually characterizing their environments. We are assessing their atmospheric pressure, their cloud cover, and ultimately, their potential habitability.
As awe-inspiring as transmission spectroscopy is, though, there seems to be a massive bottleneck built into this entire system.
How so?
Well, everything we just discussed, measuring the shadow, filtering the light through the atmosphere, it is completely reliant on the transit method.
Ah,
And the
yes.
transit method, like we said earlier, requires that perfect edge-on geometric alignment. If a planet's orbit is tilted even slightly from our perspective, it will simply do circles above or below the star's equator.
That's cool.
It will never cross the face of the star, and it will never cast a shadow toward Earth. So are those non-transiting planets permanently invisible to us?
Well, if transits were our only tool, yes. Our planetary census would be severely incomplete. We would only find the fraction of planets whose orbits just randomly align with our telescopes.
Which would leave billions of them undiscovered.
Exactly. But we have a secondary approach, one that completely ignores the shadow entirely and relies instead on the universal mechanics of gravity.
Okay.
We call it the radial velocity method.
Radial velocity. Now, to make this method work, and I think this is fascinating based on the source text, we kind of have to unlearn the classic diorama of the solar system we all built in elementary school.
Oh, absolutely, the styrofoam balls on the wire hanger.
Exactly. The model where the sun sits completely stationary in the center and the planets roll smoothly around it like marbles on a track.
Yeah, that stationary model actually violates Newtonian physics.
Right, because gravity is not a one-way force.
No, it is a mutual attraction. Sir Isaac Newton's third law dictates that for every action, there is an equal and opposite reaction. So while the star exerts a massive gravitational pull on the planet, anchoring it in orbit simultaneously, the planet exerts its own gravitational pull backward on the star.
So the star and the planet are actually engaged in a gravitational tug-of-war. They're pulling on each other.
Precisely. But because the star contains nearly all the mass in the system, it obviously doesn't get dragged all the way across the galaxy.
Right.
It just gets tugged slightly off-center. They are both orbiting a shared center of mass, known as the barycenter.
The barycenter.
Think of it like this. Imagine an adult holding hands with a small toddler, and they are spinning around together in a circle.
Okay, I can picture that.
The adult is vastly heavier, so they don't swing out very far. They mostly stay planted in the middle, but they do have to lean back and execute a tight, small circular wobble to counterbalance the toddler who is flying around them in a much wider orbit.
Ah, so the star is the adult in that scenario. The planet's gravity forces the star to wobble in a tiny circle around that shared barycenter. But wait, finding a planet by watching a star wobble sounds just as hard as finding a shadow.
It is incredibly difficult, yes.
If the star is light years away, its physical movement side to side across the sky is going to be infinitesimally small.
Oh,
Our telescopes don't have the angular resolution to see a star physically shaking back and forth, do they?
no, they don't. We cannot see the physical displacement of the star. But we can detect how its motion alters the physics of the light it emits.
Oh, okay. How?
We use the Doppler effect.
Right, the Doppler effect.
But
We interact with this constantly with sound here on Earth. Like if you are standing on a sidewalk and an ambulance comes racing toward you with its siren blaring, the pitch of that siren sounds artificially high.
exactly, because the vehicle is moving in the same direction as the sound waves it's emitting, so it physically compresses those sound waves together in front of it.
And your ear interprets those compressed high-frequency sound waves as a higher pitch.
Yes. But the moment the ambulance passes you and speeds away down the road, the vehicle is now moving away from the sound waves it emits in your direction.
So the waves get stretched out.
Right, they stretch, lowering the frequency, which you hear as a sudden drop in pitch.
Exactly. So applying that ambulance analogy to a wobbling star is where the genius comes in. Light is a wave, just like sound.
It is.
So as the star executes its tiny circular orbit around that barycenter, there will be a phase where it is swinging slightly toward Earth, and then a phase where it is swinging slightly away from Earth.
You've got it. When the star's wobble carries it